Hello, and welcome to the Ohio DOT training for its Multimodal Design Guide, or the MDG. This video is the 8th module of a 13-part training series that will span the entirety of the guide. In this video, we will focus on Chapter 7, Motor Vehicle Facilities Supporting Multimodal Accommodations. This chapter provides an overview of how typical roadway elements can be designed to support a multimodal transportation network. Other chapters in the guide provide guidance on addressing pedestrian and bicyclist travel behavior, whereas this chapter focuses on addressing motorist travel and behavior. Designers should consider all existing and planned modes during the design process and will often need to apply engineering judgment and utilize design flexibility when applying roadway design criteria. Vehicle turning movements affect operations and safety at an intersection. If conflict points are not eliminated through signal phasing or grade separation, intersection design should minimize the speed differential between users at the points where the travel moments intersect. The process for controlling the speed of turning vehicles is described in this section. The first 3 subsections discuss design controls and evaluation for right-turning vehicles. The 4th subsection outlines steps that should be taken to keep speeds low at turns. In some cases, additional treatments are recommended, as described in the final 3 subsections. The process of minimizing turning speeds is often iterative to find the right treatments to accomplish intersection goals. To evaluate intersections, designers must first select the appropriate intersection design and check vehicle. The L&D defines the intersection design vehicle as the largest standard vehicle frequently making the turning maneuver at the intersection. The intersection design vehicle must make the turning maneuver without encroaching into other lanes and without encroaching onto the shoulder or the gutter. The intersection check vehicle used for intersection turning movements is typically larger than the intersection design vehicle and makes the turning maneuver less frequently. The turning maneuver for that intersection check vehicle allows for it to swing wide and encroach into the adjacent lanes, provided there is no significant traffic disruption. In most cases, the intersection check vehicle should not encroach into opposing travel lanes and should not leave the roadway. For example, drive over curbing or leave the paved shoulder. For roadways where the most common vehicle is a passenger car, delivery vehicle, or single unit truck, designing intersections to easily accommodate larger vehicles with large turning radii can negatively affect crossing distances, exposure to conflicts, speed of common turning vehicles, and can impact right-of-way or be inconsistent with the surrounding land use context. Similarly, using a smaller design vehicle at intersections regularly used by larger vehicles should be avoided because frequent operational challenges may occur, may lead to encroachment beyond the edge of pavement or curb line, and can lead to damage to infrastructure such as curb ramps, signs, or poles. The L&D provides flexibility for selecting a different intersection design and intersection check vehicle based on the intersection vehicles and encourages that this should be done to provide the smallest radius possible to keep turning speeds low while still allowing for larger vehicles to turn. A small curb radius requires motorists to slow down to navigate the turn, which improves yielding behavior and reduces stopping distance requirements. This strategy can also help to increase the size of bicycle and pedestrian queuing areas, thereby enabling greater flexibility in the placement of curb ramps and reducing crossing distances. Once the intersection design and intersection check vehicles have been determined, 2 distinct radii need to be considered when designing street corners. The first is the actual radius of the street corner itself, and the second is the effective turning radius of the selected design and check vehicle. The effective turning radius is the radius needed for a turning vehicle to clear any adjacent parking lanes and to align itself with the receiving travel lane. These turning speeds should be controlled to a maximum of 10 miles per hour. The smallest feasible actual curb radius should be selected for corner designs based upon the design vehicle's effective turning radius. To achieve the smallest appropriate corner radius, designers should use vehicle turning software or turning templates to minimize the corner radius while accommodating the effective turning radius of vehicles. Section 7.2.4 states that where pedestrians or bicyclists are expected and the effective turning radius exceeds 15 feet due to the intersection check vehicle, the majority of vehicles, for example, passenger cars, will be able to turn at higher than desired speeds. To mitigate this, consider the following: adjust the stop bar, provide a truck apron, consider a channelized island for skewed intersections, or provide a raised crossing. These treatments are discussed in the following sections, which we will review in the next couple of slides. Truck aprons are most common within the center island of a roundabout, but should also be considered at intersection corners to accommodate the turning characteristics of larger vehicles while slowing the turning speed of smaller design vehicles. The truck apron must be designed to be mountable by larger vehicles to accommodate their large turning radius, while smaller vehicles follow the smaller curb radius along the outside edge of the truck apron. This works by constructing the outside edge of the truck apron closest to the travel lane using a mountable curb and designed so that passenger vehicles follow this mountable curb line at the desired 10 miles per hour speed. Larger vehicles, including single unit trucks, can traverse the truck apron if desired, but the control vehicle should be used to specify the effective turning radius. There are new truck apron details provided at the end of this section, illustrating different types and ways to implement truck aprons at intersection corners. Two additional treatments are discussed in 7.2. Channelized islands for right-turning vehicles and median islands or hardened center lines for left-turning vehicles. A channelized right turn may be preferable to a larger corner radius to decrease the street crossing distance for pedestrian and bicyclists. These are common at skewed intersections or other overbuilt roadways with large curb radii and cross sections. The guide covers channelized island geometry to encourage slower speeds and provide visibility between users. Chapter 4 discusses how a raised median island can be used to provide a pedestrian refuge space to cross a major street. In that situation, a minimum of 6 feet is required to accommodate a pedestrian or bicyclist waiting to cross the second portion of the street. When less than 6 feet in width is available, designers can still provide a center median, also known as a hardened center line, to channelize and slow the speeds of left-turning motorists as they prepare to cross the path of pedestrians and bicyclists. While the L&D specifies lane widths based on context and functional classifications, updates were made to provide additional flexibility for lane widths. Those updates and this section should be used to right-size lane widths to discourage speeding, reduce pedestrian crossing distances, and create spaces for sidewalks and bikeways. This is critical as every foot matters when it comes to including a pedestrian and bicycle facility along a roadway. FHWA no longer considers lane and shoulder widths as controlling criteria for roadways on the national highway system with less than 50 mile/hour design speeds. This allows for increased flexibility to implement narrower lanes on these roadways. When pedestrians or bicyclists are expected to be present, designers should use the minimum widths as described in the L&D Volume 1 figure shown here for travel lanes, on-street parking, and potentially shoulders. New notes were added and are shown in red where 10-foot lanes may be appropriate. With new construction, designers should meet preferred design values for all modes. However, more often than not, we're retrofitting roadways to provide the appropriate facilities for all modes. Options may include narrowing general travel lanes, operational changes, reorganizing street space, changing street parking, or converting parallel parking on both sides to reverse in angle parking on just one side. Section 7.8 focuses on treatments that can address speeds and volume management. People walking and bicycling are particularly vulnerable in the event of a crash, and vehicle speeds where conflicts occur are a primary factor in the likelihood of a serious injury and fatality, as shown in the graphic on this slide. Where pedestrian and bicycle facilities are provided, design speed should be equal to the legal speed. Using a design speed higher than the legal speed may cause motorists to feel more comfortable exceeding the posted speed. On existing roadways with operating speeds that exceed the legal speed, roadway design and traffic calming measures should be considered to reduce speeds and improve safety and comfort for all users. Traffic calming devices help to manage motor vehicle operating speeds and volumes by introducing changes to the roadway cross-section or horizontal deflection, pavement elevation or vertical deflection, reductions in roadway width, alterations to typical motor vehicle travel patterns, or a combination of these techniques. By managing speeds, reinforcing target design speeds, and managing volumes, traffic calming increases the comfort of a shared operating environment and minimizes conflicts between users. Another important consideration when addressing speeding issues is that often roadway speeding issues are viewed like this example. There are complaints or data that show operating speeds along this roadway are well beyond the posted speed. We need to remember, though, that streets are a part of a network, and the addition of traffic calming treatments can result in through traffic trips diverting to other nearby streets. While this may be preferable for bicycle boulevards, it may create undesirable conditions on other parallel streets. To avoid unintended behaviors, traffic calming should be considered from a roadway network perspective. 7.8.1 describes the application of traffic calming devices. Traffic calming devices are not appropriate in every context, and in addition, if the underlying roadway design encourages higher speeds, that should be evaluated first. The following sections discuss both the application and design of each traffic calming device. A horizontal deflection hinders the ability of a motorist to drive in a straight line by creating a horizontal shift in the roadway. This shift forces a motorist to slow the vehicle in order to comfortably navigate the measure. Horizontal deflection is most appropriate on local and collector streets. Lateral shifts and mini roundabouts may also be appropriate on thoroughfares and are discussed in detail in this section. Vertical deflection, which includes speed tables, speed humps, speed cushions, and raised crosswalks, are effective means for controlling the speeds of motor vehicles. Their use is limited based on the speed and roadway grade, which are outlined in this section. In addition, 3 speed hump details are provided for your reference at the end of this chapter. Research has shown that motorist speeds can be reduced by creating a sense of enclosure or by creating shared travel spaces that eliminate the perception of motorist priority. This can be accomplished through the provision of continuous or intermittent elements that reduce the effective travel lane width and narrow the field of view, resulting in a naturally slower speed environment. Designers should consider additional streetscape elements to further enforce to drivers the need to drive slowly and with caution. The last group of traffic calming measures are routing restrictions and traffic diversions. Traffic diversion strategies are used to reroute traffic from one roadway onto other adjacent streets by installing design treatments that restrict motorized traffic from passing through. These are often used on bicycle boulevards to reduce motorist volumes, but can also be used on other roadways where volumes are above desired thresholds for other bikeway types or expected pedestrian volumes. There are several illustrations in this chapter showing how to implement these diversion options. Additional sections in this chapter that were not highlighted in this video are brief and provide a quick summary of references or resources that designers should refer to for more information. Thank you for watching this video covering Chapter 7 of the MDG. For other chapters, please see the additional videos in this series.